Okay, so now we are streaming. All right, I think then we should start in time. So it's a pleasure to have Tom Britton here today, saying something about different aspects of a model. All right, I think I have to start in time. Now there's a delay from the recording. Tom Britton here today, saying something about. Okay. Yeah, so maybe, Tom, you can just say a few words about yourself at the beginning so that we know your background, and then you can start right away. So I give the word to Tom.
Okay, thank you very much. So my name is Tom Britton. I am a professor at Stockholm University, where I am at the math department, and my academic background is probability and statistics. And I have been working on infectious disease models for many years, not exclusively, but mainly through all my academic career. And I did my PhD in 1996, so I've been working in this area for quite some time by now. Thanks for inviting me to this series of talks on COVID-19, and thanks to Joan Saldana, who invited me, who I have worked together with earlier. But today I will say some words about reproduction numbers and herd immunity. So just to make sure, can people hear me and see my slides?
Yeah.
Okay, that's very good. So I will tell you some general stuff about the reproduction numbers, and then towards the end I will say a result that I have done with Frank Wall and Peter Trapman, which actually appeared in Science last week. So we're very happy with that, of course. So I know that I have 30 minutes from now, so I will try to be quick because I gave this talk last week and then I had 45 minutes. So now I will try to speed up. A lot of text on this first slide, don't worry too much about it. I think you are familiar, most of the audience are familiar with some type of infectious disease models. Anyway, I will talk about SIR type epidemics. So I am assuming that your individuals are susceptible at first. If they get infected, they become infectious, and after some time they recover and become immune. So I know that is an issue. People are wondering, do people become immune and how long does immunity last and stuff? I will not touch upon these matters. For this class of models, mathematical models, it is well known and has been studied for a long time that the initial phase of such an epidemic, you can approximate it by what's called the branching process. And the branching process is it's a stochastic model for giving birth to new individuals, and giving birth here means infecting new individuals. And the main important property with branching process is the assumption that different individuals give birth to new individuals independently of each other. And why is that true for an epidemic? Well, it is not true in general, because later on you will experience that you see some infected people, but in the beginning of the outbreak there are very few infected people. So then it is very unlikely that by chance two infected people have contact with the same third guy. So for that reason, in the beginning, and this can be proven rigorously mathematically, the epidemic behaves like a branching process if you consider a large community. And then you can sort of steal results from branching process theory. And for instance, the basic reproduction number, that notion is also related to branching process theory. This can be done for a homogeneously mixing community, but also if you include some heterogeneities, different age groups, different gender, blah, blah, blah. But it is harder to do so when you have local structures and when you consider spatial aspects. Some of these things, some of these type of heterogeneities can also be included in the framework of branching processes, but it is harder to do so. So in this talk, I will not consider these type of heterogeneities. So in what I will talk about today, there will be no households, no schools, no spatial aspects, but I will categorize individuals into different age groups and different activity levels and stuff. So let's start with the simplest case, the homogeneous case. But what comes here applies also to the heterogeneous case. I would say that there are two, well, the most important quantity of all is the basic reproduction number, and another important quantity comes here. But let me first say what the basic reproduction number is. I, like probably several of you in the audience, go to workshops on epidemic, and there is always a session about what is R0. So it's something that is discussed frequently. For a simple model, the definition is not at all problematic, but for more complicated models, it's not as clear what R0 actually is. But for the simple model, it is the average number of infectious contact that an individual has during the infectious period. That is, to me, a good definition of R0 when you have a homogeneous community. And it's important, and I will show this, illustrate this, that it depends, of course, it depends on the disease, but what people seem to forget is that R0 also depend on the community in which it spreads. So I would say that R0 is not, there is not one R0 for COVID-19, it depends on which community you consider. And the biggest, the most important result of all is that it is only possible to have a big outbreak if R0 is larger than 1. Can you see that it says R0 larger than 1, or is it hidden by some, by me or some other names here?
No, it's clearly visible, yeah.
Okay. The second, a second important quantity, in particular if you want to consider the time evolution of the epidemic, is called the generation time distribution. And this is a distribution. This here is a mean number, so it's a real number. It could be 2.5, 3.2 or something, whereas this thing is not a number, it's a distribution. And its distribution reflects the delay between getting infected and infecting others. And of course, I don't know of any disease when you infect the next person at a fixed time point. So this is always a random distribution. So you can illustrate it by a PDF or a density function or something else. And it is well known from branching process that in the beginning of a branching process, or for that reason of an epidemic outbreak, the number of infectives, so the number of currently infectious, I call that I of T, but also the total number infected, which is the community size subtracted by those who are still susceptible. So this is the total number that have been infected. They might still be infectious or they might be immune. Both these numbers grow at an exponential rate. So the rate parameter is often called small r. And there is a relation between the basic reproduction number, the exponential growth rate, and the generation time distribution. And it's called the Euler-Lotka equation. This equation means that if you know the generation time distribution and you know what R0 is, you can numerically solve what small r is. It also means that if you know what the generation time distribution is and you know what small r is, you can deduce what the basic reproduction number is. And that is what is done in statistics, because typically you can observe the exponential growth rate, and I will sort of illustrate that by either reported number of cases, but to me that is a rather questionable quantity because it depends on testing strategies and stuff. So I rely more on case fatalities. So how did the case fatalities grow in the beginning of an outbreak? From that you can estimate small r, and maybe through some other source of information, you know what the generation time distribution is, and then you can estimate the basic reproduction number. For instance, knowing this generation time distribution is quite often done using contact tracing, but that is quite hard in itself. I will not touch upon that, but I've done some work on that earlier. As an illustration, if we choose, like many people do, to assume that the generation time distribution follows a gamma distribution, then this equation simplifies to this. So here, if we know what the two parameters are, and we know what small r is, it's obvious with that we know what r naught is, and you can also compute what small r is if you know what the basic reproduction number is. So let's do this for COVID-19. I'm not claiming this to be a very serious attempt of estimating R naught, but still, I think it's an enlightening thing. So I've just chosen the generation time to follow gamma distribution, and from the literature, I looked in the literature, and it seems like the mean being 6.5 and the standard deviation being 4 seems to be a common choice. Please note that the mean here and the standard deviation, it is not alpha and beta, so you have to check. If I remember correctly, the mean is alpha divided by beta, and the standard deviation is alpha divided by the square root of beta, I think. But anyway, that you have to check. So I assume this generation time distribution to be the same in all countries. And I think that is fair to do so, because I think this generation time distribution more has to do with the virus than on how people interact. So I assume this to be the same in all countries. But what is not the same in all countries is the growth rate. So I estimate the growth rate from this relation. But I don't use this. I instead use the total number of infected, but I don't rely on how many have been infected. So instead I take the total number of case fatalities, but that will also grow at the same rate. Unless you believe that the case fatality rate changes over time, it will just be a factor of the two. So I will take how many have died. Well, it comes here. I start my clock in each country. Day 0 is when at least 50 people have died. And then I see, okay, that is my day 0. Maybe that day 53 people had died in one country. That is my C naught, the cumulative number of case fatalities, day 0. And then I see how many had died 14 days later, the cumulative number, so it is always a bigger number. And then I take logarithms and divide by 14 because I look 14 days ahead, and that will be my estimate of the exponential growth rate. So when did this happen in calendar time? Well, I looked at 5 countries. So it was typically from the starting was in the first half of March, and the end time point was in the second half of March. And I would say that in most countries, except Italy, which I have not included in the list, the effect of preventive measures on case fatalities had not started by the end of March, because most countries inserted their restrictions in mid-March, and that only affected case fatalities in April. So why did I start only here? Well, the reason I could have started earlier, of course, but quite often very strange things happen in the very early stage of an outbreak. But by the time that 50 people have died, somewhere between 5,000 and 20,000 have been infected. We don't know the exact case fatality rate, but somewhere in that order. So it's not a very small epidemic by this time. I will not talk about Norway and Denmark at all, so forget those numbers here. So forget the red ones. So here are my 5 countries. I put them in quotation because I don't think they reflect all of Sweden, all of Spain, all of UK. I think they reflect what happens in that part of the country where the epidemic started. I know most about Sweden. So here the estimate is more or less an estimate of Stockholm. I think in Spain it was mainly in Madrid, as far as I know. UK, I think it was mainly in London. So typically it is in one or a few big cities in these countries. So I'm in north of Sweden. I think the estimate has nothing to do with what happens in north of Sweden. My guess is that R0 is below 1 in north of Sweden because it's a very remote place. So I think there is no chance for a big outbreak in north of Sweden. Anyway, here are the numbers. So we see the first day that exceeded 50 cases happened to be 62 case fatalities in Sweden. And 14 days later, there was this many. And then I put in my estimate here. And then I got my estimate here. And then I said, I know what the gamma distribution looks like. So that gives me an estimate of R0. So we see that R0 was estimated to 2.5, Germany 3, Belgium 3, UK 3.5, and Spain 4.3. So we see that there is some difference in the estimates of R0 here. I don't claim these to be sort of perfect estimates. I'm sure people can do more elaborate things, but my message here is that R0 is different between different countries, but I'm also sure that it's different within different countries in different regions. That was my main take-home message. Okay, let's see here what this says. How about in a heterogeneous community? Well, then R0 has a more complicated definition, and my definition, which I think agrees with most other people's definition. What is R0 then? Well, then it is the average number of infections caused by a typical infected individual during the early phase. So it's still the early phase, which means that the vast majority are still susceptible, but it is important that we don't consider a typical person in the community, but we consider a typical infected person in the community. This means that, well, take a simple example. If half of the community are very socially active and half of the community are less socially active, then R0 is not the arithmetic mean of the reproduction number between one less socially active and one more socially active. That will not give the basic reproduction number. One should put more weight on the socially active because they will be overrepresented among the infected people in the early stage. And that can be done using next generation matrix, and you compute the largest eigenvalue. So that is contained in these type of computations. Yeah, so that comes here. So if you categorize individuals into different categories and you compute how many J individuals that one I individual infects, then you get a matrix, then R0 is the largest eigenvalue. I will not talk about local and spatial structures as I mentioned earlier. Here is a nice interpretation about R0. You can split it up. It is the probability of infection given a contact multiplied by the rate of contacts multiplied by the duration of the infectious period. And this is in particular of interest when you want to insert preventive measures and you want to attack one or several of these quantities to reduce them. So suppose you manage to, by some different combination of preventive measures, suppose you reduce R0 by a factor C. Maybe it varies with time, then you can say, call it C of T. If you do so, you get the new reproduction number, which is the old one multiplied by 1 minus C. So 1 minus C is the remaining fraction of the contacts that still take place. And if you have inserted these preventive measures for the same reason as before, you will avoid an outbreak if this new reproduction number is smaller than 1. And this is equivalent to saying that the effect, the reducing effect should exceed 1 minus 1 upon R0. So here, this thing is in the start of the epidemic, so there is no immunity in the community still. So I think, for instance, in Sweden, we inserted, I know Sweden, we are the black sheep in Europe for COVID-19. We inserted some preventive measures, which clearly reduced the reproduction number, but it seems like it did not reduce it below the value of 1. So maybe it reduced it, now I'm guessing, but maybe it reduced it from 2.5 to 1.4 or something like that, or 1.25 or something. So we still saw a rise. And if you see a rise, then the fraction of susceptibles starts declining. So after a while, with these preventive measures, so this R0 times 1 minus C in Sweden might, or in Stockholm, might have been 1.25. And in the beginning, everyone was susceptible. So it was 1.25. But after a while, people got infected. So this was reduced. And once this is, now I haven't done the numerical computations, but maybe if this goes below 0.8, then this reproduction number suddenly becomes smaller than 1, and then you start seeing a decline, and that is what we're seeing in Sweden. Whereas in some countries that had a lockdown already from the start, maybe the basic reproduction number after restrictions was below 1. Some use effective reproduction number to only consider the effect of the preventive measures, whereas some also include immunity. So have this in mind when you discuss with others. Do you include the immunity or only the effect of the preventive measures? I think there is no right or wrong here. Others call this the daily or the current reproduction number when they also include immunity. So that was, well, implicitly this for the homogeneous case. For the heterogeneous case, things are slightly different. It looks very similar, actually. If you look at this formula here and compare it to, not very visible here, but here it is. The effective reproduction number for a homogeneous community at some calendar time t is the original one multiplied by the remaining fraction of contacts multiplied by the fraction of susceptibles. Now, if you have a heterogeneous community, this changes. The only change here is that I have a sub-index script I of t and I have a sub-index script I of t. So what is that? It's not rigorously mathematical, but it's a symbol. To me, it's a symbol representing the composition of individuals that get infected around time t. So how many people on average do people infected at around time t infect? Well, that is R0, but of the group that got infected here. So in the beginning of an epidemic, typically the most socially outgoing people get infected. So they typically infect more people. So they have a bigger R0 than the people that get infected later in the epidemic. So this thing here actually decays with time. Here's similarly, this should be the fraction susceptible among those contacted by this group. But I think that is maybe of less importance. So I would say that maybe it's fair to approximate this by the overall fraction susceptible. So an approximation of the current reproduction number is as before 1 minus c times s of t, but it is R0 among those that get infected around now. And this quantity here, I would say that decays with time typically. So in the beginning of the outbreak, the people that get infected, they infect more people than those that get infected later. So that there is another effect which brings down the effective reproduction number, which I think sometimes is less thought of. And one reason for this is that it's very hard to know what it is, except that it should be smaller than in the initial phase. So the effect is that fewer will get infected in a heterogeneous situation as compared to homogeneous. And I've tried to illustrate this on the next graph. So here the blue plot is for a homogeneous community, and the red plot is for heterogeneous. If I remember correctly, I divided the population into two categories, 50% of both. One is more susceptible and the other one is less susceptible. And I calibrated the two by having the same R0. So these two populations have the same R0. And we see that initially the curves follow each other, but eventually the rise is smaller in the heterogeneous case. So here, yeah, so that is the case. And in the overall fraction infected is also smaller in the heterogeneous compared to the homogeneous case. Nearly always the homogeneous case is the worst case scenario. Okay, so if you have a set of preventive measures, sooner or later it will have a reproduction number which is below 1, because eventually either the preventive measures are good enough or else the fraction susceptible will start declining. So eventually this will happen. And this means that whenever this happens, it means that with the current preventive measures, there is sufficient immunity for the epidemic to die out.
Mm.
But this is not herd immunity. This is immunity. Here the immunity is enough for the current preventive measures, because when this happens, the epidemic will start declining and soon die out. Herd immunity, that is, if this is true, once we have gone back to normality. So if we go back to normality and set C equal to 0, so we stop all preventive measures, if there is still no second outbreak, that is when we talk about herd immunity. A related question is, of course, if we are in this situation, how much back towards normality can we go without having this exceeding 1? But I will not touch upon that question. So the classical herd immunity comes from vaccination, and that is what fraction, I call the fraction age for herd, what fraction has to be immunized by means of vaccination before an epidemic comes around in order to avoid an outbreak. That has been studied for a long time, and it is known that if we vaccinate uniformly, we have to vaccinate at least this many, assuming the vaccine is perfect, by the way. We have to vaccinate this many in order to obtain herd immunity. So if R0 is 2.5, it says that you have to vaccinate 60%, and if you do so, you will have herd immunity. So this is called the critical vaccination coverage. This was if you vaccinate uniformly. It has also been studied, a bit less, but still by many authors, including myself, that maybe you can do better vaccinating optimally. There are some strategies. One is called the acquaintance vaccination strategies. For instance, in social networks, in particular if they're scale-free, it's known that if you vaccinate uniformly, you more or less have to vaccinate everyone. Whereas if you do some optimal vaccination strategy and vaccinate the super spreaders, it could be enough to vaccinate only 1%. So this has been known for a long time as well. Now, we are not interested for COVID-19. We're not interested in the classical herd immunity because we have no vaccine. Mm-hmm. So it's a slightly different question for this for COVID-19. And in fact, I think this question is the first time that it has ever been posed. Mm-hmm. And the question is, how many or what fraction must have been infected during a mitigated outbreak in order to avoid a second outbreak once we relax all the preventive measures? I don't think that question has ever been asked before, because I don't think, at least not on a global scale, people have changed behavior such that the epidemic is on decline now, more or less worldwide, even if we're far from the final sizes that we would expect without any preventive measures. So the question that we addressed in this paper was that was the following. Suppose you have mitigation or lockdown and you gradually exit towards normality. Then we ask ourselves, at what stage will herd immunity be reached, assuming that we know what R0 is? And let's assume that R0 is 2.5. That's not important, but I will take that as a numerical example. Then the first natural guess would then be to say, well, it should be, as for the classical herd immunity, so it should be 1 minus 1 over R0, so it should be 60%. Is that true? This is true if immunization is uniformly distributed, just like the vaccine. However, after disease spreading, immunity is not uniformly distributed. And in fact, the effect is that it's enough with a substantially smaller level than 60%. I don't claim we know what it is. We have a toy model, which I will show, where it says 40 to 45%. But independently of us, there was another group who studied variation in susceptibility, and they said that if susceptibility varies greatly, herd immunity could be at 20% or even lower. But they don't say that this is the case. It's more an illustration. Why is this the case? It is the case because when immunity is obtained by disease spreading, it is more efficiently distributed in the sense that the socially outgoing people are more likely to get infected and hence more likely to be immune. And this has been known for quite some time, but no one seemed to have realized this effect to be useful when we have a disease spreading under mitigation or suppression. So I guess we and Gabriela Gomez were the first to sort of make this connection to this is useful when we have an epidemic with mitigation. So here is our illustration. I see that my time is out. I have one more or two more slides. I will try to finish very quickly. So we divided people into 6 different age groups and mixing according to a social study of how people interact. And then on top of this, we assume that individuals can be categorized into 3 types of individuals. The normal people making up 50%, and the less socially active 25%, and the more socially active 25%. Of course, this is not true, but maybe it reflects somehow reality and somehow picks up these features from network characteristics that's known. So in total, we have 18 groups, and R0 is a dominant eigenvalue of this next generation matrix. And you can solve for this. And then we said, how about prevention? Well, we simplified life by assuming that all groups reduced their contacts by the same factor. I don't know if this is the case, but this is our assumption in in the model. And then from that we computed as follows. Suppose we reduce spreading by some fraction alpha, and then we let the epidemic run, and then we drop alpha to see is it possible for a second wave. If this is not the case, where this alpha is the sharp value when it stops being having risk for a second wave, we compute how many were infected in that situation. And here is the result. Let's look only at the lower row and R0 2.5. The classical herd immunity says 60%, whereas for our model, it said it should be around 43%. If we instead, so this was assuming that preventive measures were put in at the start of the epidemic and kept all the way through. How about if we look more like reality? So maybe the epidemic started around February 15, restrictions were put in place March 15, and all restrictions were lifted the day before yesterday. Then here would be the different outcomes depending on the amount of preventive measure. Blue is no preventive measures. We see we have a huge outbreak and then it stops. Restrictions are lifted here. This is June 30. Here we have mild restrictions, not as big outbreak, and nothing happens when restrictions are lifted. Yellow, more restrictions. We lift heavier restrictions, and here we lift them. We see that there is no second wave really, but it does not decay as quickly. Whereas if we have very strong restrictions and we lift them, we see that the second wave is almost as big as the first wave. And in terms of final sizes, this is a little bit surprising that here we have very strong restrictions and lift them. Here we have slightly milder restrictions and lift them. And we see that the end product is that you're worse off with strong restrictions and then suddenly lifted. So that's a little bit surprising. And then we looked at the situation with gradual lifting, and then this difference becomes smaller. And if you make the gradual lifting even longer, the two will coincide. But anyway, here we see that with this curve, we reach somewhere around 45% getting infected, whereas the classical herd immunity says that 60% is needed for herd immunity to obtain. Whereas here we see that it really happens at 45% or even lower, because by this time all restrictions are lifted and the curve is more or less horizontal. My last slide is that the disease-induced herd immunity is substantially lower than the classical one. How much lower, that we don't claim to know, and I think it's an important task to try to estimate this more for more realistic models. You can add more heterogeneities, for instance, households, schools. I think most of them that we have thought of would make the difference bigger, but not all of them. However, one thing which will not make the bigger difference, which could make the difference smaller, is if the restrictions that people take differ between the different groups. Then you could have, for instance, closing of schools. That could make the difference actually smaller, I think. But this is, you need to do investigation of this. I think that ends my talk, and sorry for talking 5 minutes too long.
Yeah, thank you very much, Tom, for the very nice talk. So, yeah.
I will. Shall I stop sharing, or maybe I keep it up with some?
Yeah, please for a moment. Then you can come back to sharing when there is a specific question, maybe on a slide or so.
Okay.
Yes, I would like to open the discussion. So please, if you can, use the Zoom indication that you want to ask a question, or if you don't know how to do that, then just switch on your microphone. Yeah, I think you should be able to do that. Okay, so I would like to start the discussion. Are there any questions? Okay, if not, then I would like to start the discussion. Of course, you can imagine that this kind of herd immunity is quite controversial. You are rightly saying that there is no vaccine, so it's more or less clear that eventually, if there would be no vaccine in the future, herd immunity would be more or less the only thing that could stop the disease entirely. With this, I would agree. But I think the question is at the moment that you want to delay the disease dynamics until a vaccine is available. And that is a little bit a different question than the one you had in your example. So would you still say that the measures taken by the different, let's say, for example, European governments was effective in the sense that it could delay the outbreak, the big numbers of outbreaks sufficiently such that we will have now gained time in order to create a vaccine in time? What would be your answer to that?
Well, first, let me explain one thing. So this is not a promotion for aiming at herd immunity. Maybe I should have told that early on. So a direct consequence of our result, which is good news also if you don't aim for herd immunity, is that even before herd immunity, the effect of the immunity is bigger due to this heterogeneity than people would have thought. So even suppose that if only 10% have been infected, we are clearly not at herd immunity. But if we take these heterogeneities into account, the effect they play on reducing the spread is bigger than one would think if you just thought of classical immunity. So I think it's a good news. Even I don't think, I'm not promoting aiming for herd immunity, but so it's good news also below this herd immunity. And in terms of policies, I know less, but I mean, of course, all countries want to minimize the number of severe cases and case fatalities, and postponing such case fatalities probably is a good idea. I think it's very good to do so. Of course, you have to value it. You have to. There are two things that, of course, if you close down society for a year, then you will have no case. You will have very few case fatalities.
Yeah.
But there is another high price for the economy, but probably there's also a high price for other medical things. I mean, I heard on the news today that obesity has increased in England because of school closing among children. So I mean, there are two ways. Either you suffer by a lot of case fatalities, or either you suffer in some other respect. So you have to find a balance, but where this balance is, I don't know more than you do. So I don't know what is a correct measure. I think Sweden, we have been criticized quite a bit. Probably some of the criticism is correct. One thing that I would defend, without having sort of any scientific knowledge for it, that is that we kept schools open. And that is one thing that I think I support our government and the Public Health Agency, and they say that closing schools for 3 months has so many other negative effects on on public health and economy and whatever, that even if it costed us a few more case fatalities, maybe it was worth it. But in other respects, maybe we should have put in more efforts.
Just a clarification question. In your model, you assumed immunity was complete. So once you are infected, you have total immunity.
Yeah. Yeah, I mean, so I know that is something that's discussed. So in a probably we could modify the model saying that 90% get infected. I think we would have still the same qualitative results, but rather than 43%, maybe it would be 48%. But we did not go into those technicalities because we wanted to have a sort of a simple type of result. But I know that people are discussing this now in Sweden. I hear that people are talking about two different types of immunities. One is antibodies, but then there could be some mild or asymptomatic cases that don't have antibodies, but they have something called T-cell immunity. I don't know about that stuff. So,
yeah. Okay. Any other questions? Okay. Yeah. Please.
Suppose you have an opposite situation where everybody is equally socially active normally, but different categories respond differently to preventative measures. For example, some people still have to go to work, and so they have as many contacts as before, but other categories maybe sit at home and don't have any contacts. Would you expect qualitatively the same result? How would you expect the results to differ?
That's a good question. I think an even more interesting question would be to assume that people are not from the start equally socially active. You said let's assume that they are equally socially active, but then they respond differently. An even more interesting question would be that they are not socially the same, but they also respond differently. That would be an even more interesting question.
But yeah, I just want to simplify it.
But let's go to your question. I guess that the effect we found would be much smaller in your situation, because once you go back to normality, there is no heterogeneity. So probably, maybe there is no effect whatsoever in your situation. If you go back to normality, I mean, because if you go back to normality, according to your model, everyone was the same. So it doesn't really matter which fraction had been. It doesn't matter where immunity is spread in that case.
Any other question?
So, Tom?
Yes.
Yeah. So, if I understood correctly, the idea is that the social heterogeneity that initially increase are not, because we have super spreaders. At the same time, reduces the value of age, the immunity that we need to contain the epidemic at the end, because these initially spreaders are already infected and then they become immune. This is the idea. So it's something bad at the beginning of the epidemic, but it's something good at the end of the epidemic. Is that right?
Yes, so it's a very basic, I mean, it's nothing deep. You're completely correct. I mean, you can think of HIV. I was not into science at that time, but I still remember the predictions of HIV, and it said that in a couple of years, 50% of the globe will have HIV, because they forgot about the heterogeneity in terms of sexual activity. In the beginning, the people that got infected in the beginning, they were highly promiscuous. And then they just extrapolated, assuming that everyone was like that. And then it would spread like hell, but it was just a small fraction that were sexually active. So once they got infected, the growth rate declined or more or less stopped after that. So it's the same type of effect, although not as pronounced as for sexually transmitted infections.
Then I would like to give the word to David Alonso.
Yeah, thank you for your clarifying talk. I had this feeling that there was something there about herd immunity and so on that had to do with heterogeneity, like working with ABMs, so agent-based models. But of course, then they are so difficult to analyze, like mathematically, that sometimes you say maybe there is some error or there is something. But I mean, I finally got the point about the importance of heterogeneity and how heterogeneity reduces the amount of people, so herd immunity and so on. But one technical thing I want to know. So when you talk about next generation matrix, it means that the model you had in mind is ODE based, right?
Yes.
So because at the beginning, okay, perfect. So and the other question has to do with ABMs. So do you think ABMs that are very difficult to program, very difficult to analyze, have a role to play in controlling outbreaks and in giving advice to policymakers and so on and so forth?
I think it's very good to use a number of different models. So I think I usually use simple models. I often use stochastic models because probability is my background. But deterministic model clearly have a role to play there as well. And these very complicated deterministic or semi-deterministic or semi-stochastic models that the Imperial Group do, they have a lot of structure of different kinds, also have a very important role to play. And I think also agent-based models have a role to play. And all have some advantages and all have some disadvantages. But I mean, if you do, or not the same person, but different groups use different models, if they come to the same type of conclusion, I would feel sort of, it seems like the results would be reliable. Whereas if they come to different type of conclusion, that is when discussion should take place, and you should sort of compare the results and try to understand why they are different, and then try to calibrate them to data to connect it more to the ongoing epidemic. So I think it's good with several different type of models. The disadvantage with, I guess, agent-based and also the models of Imperial Group and others is that they have so many parameters. So there is also, and they try to give the best estimates to these parameters, but you never know if they're completely correct, the estimates. And also you don't know which parameters are really influential and which don't matter. So I guess that is always a problem when you have many parameters. And the problem, of course, with simple models is that they don't mimic reality. Even if you choose the parameters correctly, they don't mimic reality very well.
Yeah. Then I would like to give the word to Steffen Bauer.
Thanks. And thank you for your nice model. I like to play with it a lot. You made these three groups of activity. Did you make some experiments how the dependence, for example, of the alpha parameter, where there's a second wave, towards the kind of these heterogeneities, for example?
No, maybe that is something we should have done more. I mean, it was rather arbitrarily chosen, these three groups of activity levels. And I mean, so we chose 3 activity levels. Maybe it would be natural to assume more a homogeneously spread activity, but then we could not categorize them into discrete entities and compute the mean offspring matrix. So that is why we chose a discrete number. And then we said maybe most are sort of in the middle, and then some are on the side. So that's why we chose 50%, 25%. And then the third question was, okay, how much different should they be? And we said that the less socially active, they should be half as social, and the more socially active, they should have double social activity. And all this was very arbitrary, and we don't claim, I mean, that is something, it would be interesting to calibrate this better to reality. And I would assume that there are social studies, for instance, from network theory, sort of looking at how the heterogeneity in activity works. So I encourage more work in that area, and I'm possibly thinking of doing this, although it's not my strength to do things in a fully realistic way, so I'm not sure if I will, but possibly I will try to do it, but better if someone else does it.
Any other question? I don't see any hand raised. So use your microphone if there's another question.
There is a difficult question, I guess. So according to your results, those countries where the lockdown measures were stronger are more at risk of a second wave. So how could you communicate this to policymakers?
Well, I think they are aware of this. I mean, countries that have very strong lockdowns and very few infections, I think they are aware of the risk for second waves. Whereas I think, I mean, countries that have had big outbreaks, for instance, in the Madrid region, in Lombardia, and also Stockholm region, I think the risk for big second waves is much smaller, but of course the price they have paid already is very high. So I'm not saying that that was the correct way to do it, but I mean, if I was to bet on a second wave, will it take place in Rome or in Milan? I would put my money on Rome, because very few have been infected there, I think. So I think immunity will play a role, but of course all of us hope for a vaccine, but that seems to take some time. But it could also be much better treatment, and from what I understand, that could happen. So I mean, it could very well be, but that no country will experience big second waves, but there is a risk for it, that's for sure.
Thank you.
Maybe a last question I have is a kind of behavioral question. So if you would take into account additional feedback loops, like, you know, that people seeing a certain behavior and then mimicking it, or seeing a certain danger, and then, for example, switching activity groups, speaking in terms of your model, do you think that would also be worth investigating? So
I think one thing that, we assumed that all activity groups reduced their contacts by the same fraction, and maybe it is more realistic to assume that the highly active reduce it more.
Yeah, for example.
So probably that would be a more realistic model. But then how much more? It would be nice to have some type of data supporting, of course, even if it's some type of data making a sort of a qualified guess rather than just saying, I assume this. So some type of data supporting it would be nice. And then I think the conclusions could be of great value, I think.
Yeah, I mean, I agree with that. You know, having more data to parameterize the models is useful in any case. You did that at the beginning of the talk, but I'm sure there is much more scope on different levels for parameterizations and using different types and sources of data. Yeah, so yeah, that would be clearly also one line of investigation which could be done.
Yeah.
Just
Okay.
a short question, Marcus.
Yep.
Just a short question. I would like to understand this point of how did you parameterize the activity? Saying, for instance, if I understood correctly, the number of people that meet in a certain amount of time or in a given amount of time, or
so we had age groups,
okay.
and there we used a social study on the rate at which children meet with adults. So we took that from a social study. So that is sort of based on data, let's say. But then we said, let's not assume that all children behave similarly and all teenagers behave similarly and all adults. Instead, we categorized each age group into 3 different groups. And we said that they have different contact rates, but all of them had sort of chose their contacts according to the same law from this social study, let's say.
Thanks.
Yeah. Okay, thank you for that clarification. Are there any other questions? Yeah, well, if not, then I really would like to thank you again, Tom, for this excellent talk. I would like to remind everybody, if you want to see the talk again, going through some details of the talk, you can find a recording on the stream service of YouTube. The link is in the blog we have on our webpage. And I hope also that we get the slides from Tom, and I will also put them up on the webpage so you can look at it again. Well, I would like to thank you again, and also thank you and also thanks to the audience. And I wish everybody a pleasant day, depending on where you are in the world.
Thank you very much.
Yeah. Bye.
All right.